Good afternoon, everyone. I'll be sharing about what our first Galaxy group has been up to for the past year. In case you're wondering, I'm presenting here today because Michele is on his parental leave. The goal of our first Galaxy group is to understand and characterize the first galaxy and their evolution. For the past year, we can categorize our works into 3 domains. One is to look at galaxies at the epoch of the reionization to study their bulk properties such as UV luminosity functions, UV slope, and mass size relation. The other domain is to study quasars at high redshift, while the last is to study gamma ray burst population and metallicity in homogeneity. This is the list of our publications from last year. We are quite a small group, but we managed to get a number of publications done. Let me first talk about our work with galaxies in the epoch of the reionization. We now finished the box survey, which is a multi-band imaging parallel survey with the Hubble telescope. We compiled all the bulk images and include the images from other parallel surveys into a master catalog called the SuperBulk. So please see Morishita 2020 if you are interested in the data. In Robust Bosony 2021, we analyzed the candidates in the SuperBulk catalogs for their physical properties. We find no trends of UV continuum slope with redshift, and that the size luminosity relation extends all the way to the bright end. Of course, one of the main goals for bulk is to characterize the luminosity function, especially at the bright end. However, before we do that, we have evaluated the existing methods that determine the luminosity functions. We found that in the presence of flux scatters, some methods may derive luminosity functions with larger bright end density than the intrinsic values. This is very relevant to our high redshift candidates, where uncertainties in the measured magnitudes are quite large. So what I show you at the top panels are the luminosity functions derived from a mock experiment, while the panels at the bottom show the luminosity functions for redshift 5 galaxies in the goods field, where we added noise at varying degrees. As you can see, if when the flux scatter is above 0.2 or 0.3 magnitudes, some method derive luminosity functions with excess at the bright end when compared to the true luminosity function or the input luminosity functions. So please see the upcoming paper if you're interested in more detail. Another issue that we look into is how to better characterize contamination of high redshift galaxies. This work is led by our new PhD student, Hilmi. The idea is that previously the contamination rate is calculated by taking into account of the signal to noise of the image and the selection criteria considered. Specifically, we usually inject SEDs of low redshift galaxies, or the blue dots are shown in this diagram. And so we inject them into the color diagram and see how many of these blue dots leak into our selection windows. However, this method generally ignores the fact that there can be local clustering or a local void of redshift 2 galaxies in any given image. So with this idea, we are trying to see if we can better constrain the contamination rate by taking the number of redshift 2 galaxies in the image into account. So we started by testing for cross-correlation between the 2 redshift samples in the goods field. Our preliminary results show that there is a correlation between the 2 redshift samples. So this likely indicates that in an overdense region of redshift 2 galaxies, there is larger contamination rate indeed. So we hope to apply this correlation into our contamination calculation. So now let's move to the topic of quasars led by our recent graduate, Kevin Run. So in his first paper, Kevin looked at the environment around bright quasars at redshift 6. Observationally, we now have discovered more than 100 quasars at redshift 6 and beyond. So theories and simulations predict that these bright objects are tracers of extreme overdense regions, and that there should be a local clustering around the most massive black holes. However, observations so far yielded no conclusion on the local clustering of quasar. So Kevin looks into this by using dark matter halos in an n-body simulations. He populated the dark matter halos with quasars and galaxies using really simple luminosity versus hollow mass relations. The key parameters are the scatter in the luminosity hollow mass relations for both quasar and galaxies, and the duty cycle of the quasar mode. He found that in order to have models that match with the models with high duty cycle that match the observations, which is all the regions above this line number 2 here, the scatter in the galaxy luminosity relation has to be greater than 0.3 dex. On the other hand, if we allow the duty cycle to be as low as 1%, then there's essentially no restriction on the scatter of either galaxy or quasar luminosity halo mass relations. However, this situation of low duty cycle is less likely, as it would be difficult to create a supermassive black hole at early times with the low duty cycle. So in the subsequent paper, he extends the models to explore the evolution of quasar luminosity functions with redshift, and found that all models with any duty cycle can reproduce the current observations. The predictive power comes at redshift 8 and above, as shown in this red and purple, blue and solid lines. So this highlights the importance of the upcoming wide area surveys, such as those with the Nancy Grace Roman telescope. Next, I'll be presenting the works by our first year PhD student, Benji, on GRBs and metallicity in galaxies. So one advantage of studying gamma ray bursts is that they provide really good opportunity to study both global and spatial metallicity of the host galaxies at high redshift without the need of lensing. So this is because when gamma ray burst happens, we can look at the absorption line metallicity along the line of sight of the gamma ray burst from the afterglow of observation. However, because the afterglow fades quickly, after a year or two of the burst, we can obtain the host galaxy global metallicity from the typical emission line method. So with this idea, Benji looks into the relationship between the two metallicity, the absorption line metallicity and the emission line metallicity, and see whether we can use them to constrain the gamma ray burst formation pathway. Specifically, in a collapsal models, it predicts that gamma ray bursts only occur in massive stars with metallicity less than some threshold value. So with this collapsal model and and the use of illustrious TNG simulation, he came up with this predicting plot for the relationship between the two metallicities. At any given threshold metallicity of the gamma ray burst. Currently, there's only one observational measurement, but it would be very exciting to see the upcoming results. From what we know, there will be at least 10 more measurements from JWST next year.
2 minutes.
So in the second work, Benji introduces a mathematical tool called geostatistics as an alternative approach to study metallicity maps of galaxies beyond metallicity gradients. So the specific technique that he is exploring is called a semi-variogram, which it is a technique that is used widely in the field of gold mining and weather forecast to see how the gold percentage change in the mining area, for example. But let's see how we can apply this to galaxies. So in his example application, let's say that the metallicity, let's say that a galaxy has a metallicity field that consists of two components. One is the gradient and the other is the spatially varying random component. So after we subtracting the gradient component off, then we can generate this semi-variogram that looks something like this. The advantage of this is that we can see that the measurement error can be disentangled from the random fluctuation in the metallicity field. And he plans to show that this could be a useful tool to compare with models, for example, to show how metals ejected by a supernova diffuse through ISM over time. So in the upcoming year, we hope to see more developments with JWSTs, where we are part of several programs. We expect to see the properties of the first galaxies in details beyond the bulk properties, such as number counts. And so I'll finish with this summary slide, and please let me know if you have questions, either here or on Slack. Yep. Thanks, everyone.
Thanks, Nicha. We have time for questions. Let me check. Feel free to just raise your hand and ask your questions on Zoom as well. Do not see any yet. So if anyone thinks of any later, just feel free to write them on Slack.
I had a question, Andrew.
Yes, go ahead, Lisa.
Yeah, this is really great to see. What are your plans for the future? Going out in redshift, particularly JWST and that sort of thing.
So we have one project to observe the spectrum of the high confidence candidates at redshift A. So we don't know what we can see. We hope to see at least some lines.
Do you expect to? Yeah. So I'm just wondering what you expect to detect with those and how it will proceed the progress in this field.
We hope to see Lyman alpha emission lines, and then to see what are to see or not to see would give some information. But
do you think we'll be able to do like anything to do with chemical abundances or anything like that? Like, will we be able to drive any properties of the galaxies at Z of 8?
If we see continuum in the, if we can observe.
That would be hard, hey?
Yeah.
So. Okay, thank you.